Hey Math 135, what's up? In this video we're going to be looking at some extra examples from section 7.5 on conditional probability and independent events. In number 1, they tell us that A and B are independent events, so that's important, with the probability of A complement is 0.4, the probability of B is 0.6, and they want us to find the probability of A intersect B complement. Now, since A and B are independent events, then one thing we know is that the probability of A intersect B is equal to the probability of A times the probability of B. That's one of the facts that goes with independent events. If we also have that A and B complement are independent, then we could use that same fact then we can use that same fact to say that the probability of A intersect B complement is equal to the probability of A times the probability of B complement. And we can find both of those probabilities pretty quickly using our complement formula. The probability of A will be 1 minus the probability of A complement. And similarly, the probability of B complement will be 1 minus the probability of B. And so if we're able to say, I guess this is still kind of a question here, if we're able to say that A and B complement are also independent, then our probability here will be 0.6 times 0.4, which I think is 0.24. All right, so I think that's going to end up being our answer here, but we should check. We should check to see whether or not A and B complement are independent when A and B are. And I think the only real way that we can do that is to maybe make a Venn diagram. All right, so we'll have our Venn diagram with our two sets A and B. The probability of the intersection is the probability of A, which is 0.6, times the probability of B, which is also 0.6, and that gives us 0.36. So that's the amount that goes in the middle. That's our intersection. The entire A circle. Now, there's been some confusion about this that I've noticed on quizzes. The A region is not the crescent part. I guess that's the piece that the letter A is in, but the A region is the entire circle in this Venn diagram. This crescent part is actually A and not B, or A but not B. That's what that crescent part is. The A is the entire circle. All right, A itself is supposed to be 0.6. We've already got 0.36 over here. That leaves 0.24 in that part of A, and also 0.24 in that part of B by a similar argument. B, the probability of B is also 0.6. When we add all those things together, inside the bubble, the probability of A union B, or inside both bubbles, if I add everything up, that's 0.84. And that leaves 0.16 on the outside here. Now, when we're looking for A intersect B complement, that's this region right here. So we can see that we can use the Venn diagram also to see that the probability of A intersect B complement is 0.24. And actually, we're just kind of verifying. That's how we actually verify that A and B complement are also independent. We use the fact that A and B are independent to get our Venn diagram filled in, and then we use our Venn diagram to verify the fact that when A and B are independent, then A and B complement are also independent. And we could also show that A complement and B are independent. and also A complement and B complement are independent. All right, whenever A and B are independent, then all the complements, all the mixtures of A and B and their complements are also independent. All right, in 2, we want to determine whether the events A and B are independent. That's where we're going to use our test. Basically, what we're going to ask is the probability of A intersect B equal to the probability of A times the probability of B. They gave us the probability of A intersect B. So we need to find the right-hand side here. Using our complement formula, the probability of A is going to be 1 minus the probability of A complement, which is 1 minus 0.1, which is 0.9. And again, using the complement formula, the probability of B will be 1 minus the probability of B complement, which is 1 minus 0.3, which is 0.7. And so, let's see, on the left-hand side, the problem told us that the probability of A intersect B is 0.63. And I guess the question is that equal to 0.9 times 0.7? Yeah, it is. That's not a question, that's true. All right, so yes, we use this test for independence to verify that A and B are independent in this case. We could have also, I guess another strategy that you could have taken is to find the probability of A complement intersect B complement and see if that's the same as the probability of A complement times the probability of B complement. Using the complement form, I take it back. Sorry. This is going to be harder than I thought it was, so never mind on that. That's probably going to be a harder thing to check. All right. For number 3, a pair of fair dice is rolled and the sum of the numbers is noted. So we're looking at what the dice add up to. Determine the probability that one die resulted in a 6 given that the sum is 7. So we have a conditional probability here. We have a conditional probability. Let's look at this. Let's just name a couple of events here. We'll let A be the event that one die is a 6. And B will be the event that the sum is 7. Right, there's a couple of things that we could do here. We're finding the conditional probability. What they're asking us to do is to find the conditional probability, probability of A given B. And there's a couple of formulas that might work for us. There is a counting version, the number of things in A intersect B divided by the number of things in B. And there's also a probability version. Probability of A intersect B divided by the probability of B. We're able to use the counting version in this case because we're talking about a uniform sample space. When we roll a pair of fair dice, we have a uniform sample space here. So we can use the counting version. And I think when we have this kind of problem, I think we can just write these things down using the, we can use the roster notation. And I think it's best to start with B. Usually you start with your conditional event. B is the conditional event here. So we're going to start with B. The sum is 7. We've got, let's see, 1 and 6, and 6 and 1. There's 2 and 5, and 5 and 2. And then 3 and 4, and 4 and 3. All right, so the number of things in event B is 6. For A intersect B, we don't even really need to write down A. We can just look at B, look at all the things in B, and see which one of those have one die as a 6. A intersect B is a 1 and a 6, and a 6 and a 1. I kind of didn't want to write down A because A was going to have too many things. So if we can start writing down B and then just pick the things out of B that are also in A, the dice rolls in B where one of them was a 6, we can get A intersect B by doing that. All right, so it's easy to see there's two things in A intersect B, and so our probability here is 1/3 if you reduce the fraction. You don't have to necessarily reduce the fraction, but this one was a nice reducible fraction. And we use our basic conditional probability formula to get that done. All right, moving on to number 4. A biologist finds that 45% of fruit flies have short wings and 25% have eye defects. Assuming these two events are independent, what is the probability that a randomly selected fruit fly has neither short wings nor eye defects? So I guess we could say, I don't want to use S. Let's just use H for short wings. All right, so H would be the event of short wings. I don't want to use S because that's sample space, so I'll just use the second letter there. Short wings. And E will be the event that the fruit fly has eye defects. And the problem told us that a few things. First off, they told us that the probability of H, probability that a fruit fly has short wings, is 0.45. The probability that a fruit fly has eye defects is 0.25. And then they also told us that those two events are independent. And so we could say that the probability that a fruit fly has short wings and eye defects is the probability that they have short wings times the probability that they have eye defects. All right, so let's see. What's the problem asking us for? The probability that a randomly selected fruit fly has neither short wings nor eye defects. So another way to say that is not short wings and not eye defects. So they're asking us, let's see, the probability of H complement and E complement. And up in the first batch of problems, we determined that whenever our events are independent, then their complements are also independent. So the fact that H and E are independent, it also tells us that H complement and E complement are independent. So we could say that the probability of H complement and E complement is the probability of H complement times the probability of E complement, and then use our complement formulas. Let's see, H complement will be 1 minus 0.45, so that'd be 0.55. And E, probability of E is 0.75, so the probability of E complement, the probability of E is 0.25, so the probability of E complement is 0.75. And when we multiply those things together, and I guess I'll round to 3 decimal places because that's what it looks like a lot of the WebAssign problems ask you to do. Or I'll just give it to 4 decimals since that's the exact amount. 0.4125. I guess rounded to 3 decimals, that'd be 0.413. All right. Now, just like we did in the first problem, we also could have used our independence of H and E to find out that the probability of the intersection here is 0.45 times 0.25, which is 0.1125. And since we have the intersection, we could fill in a Venn diagram. I think probably the main challenge here, is deciphering the neither nor. Neither nor means not that one and not the other one. Moving on to number 5. A box contains 4 blue and 5 white marbles. A marble is selected at random and its color is noted. If it is blue, then it's replaced. Otherwise, it's not. A second marble is selected and its color is noted. In part A, find the probability that the first marble is blue and the second marble is white. So there's a conditional probability formula here. So we'll call our event, let's see, first blue. How do we do that? First blue and second white. That's what we'll do. So there are a couple of probabilities. The product rule here. Now these aren't independent events. When our events are independent, the product rule is a little bit nicer. But when they're not independent, the product rule says that the probability of the first blue and the second white will be the probability that the first is blue times the probability that the second is white given that the first is blue. So that's the product rule. Now, the probability that the first is blue, we've got our box. Our box has 9 marbles total, and 4 of them are blue. We're pulling a marble out at random, so all the marbles are equally likely to get chosen. We can use our basic probability formula and say, hey, the number of ways to pull out a blue marble is 4. The number of things that can happen is 9. So the probability that the first is blue is 9. Now, the probability that the second is white given that the first is blue. Since the first one is blue, we're going to put it back in. All right, since the first one was blue, we're going to put it back in. So in that second round, there are 9 marbles. There are still 9 marbles in the second round, and then 5 of them are white. So the probability that the second one is white, given that the first one is blue, is 5/9. Now, we didn't use anything fancy. We didn't use any fancy formulas to find that. We just kind of thought about it. What's our sample space now? For the second round, what is our sample space? Since we put the blue marble back in, there's 9 marbles. Or what's our selection set? It's another way to think about it. There's 9 marbles, and 5 of them are white. So the probability that that second round is a white marble is 5/9 in this case. Okay, so the multiplication here gives us 20 over 81. And there's a decimal approximation for that, but I'll let you do that on your own with your calculator. Let's see. Part B, find the probability that at least one white marble is selected. Now that one's a little bit more challenging to do with just a product rule. I think we're going to save that one for just a second from now. We have another tool that might help us here to get B done. In C, we want to find the probability that the second marble is blue, given that the first marble is white. So that one we can do in a similar way to the one in part A. We're trying to find probability. This is a conditional probability. Find the probability that the second is blue, given the first is white. And one of our basic conditional probability formulas would say find the probability that the second is blue and the first is white divided by the probability that the first one was white. Now, I think this conditional probability is a little bit overkill here. Just like up here, we just kind of used our thoughts to figure out that conditional probability. I think that this conditional probability formula is a little bit overkill. All right, we can just kind of think about this one. If the first one was white, we started with 9 marbles. If the first one was white, we're not going to put it back. And so when we go to pull that second marble out, now there's only 8 marbles to choose from. Kind of our new adjusted sample space is that there's 8 marbles. 4 of them are blue and 4 of them are white. And so there's a 4 out of 8, or 1/2 probability that the second one was blue given the first one was white. Now, I think it might be easier for us to see some of these if we draw a tree diagram. All right, so let's go ahead. We've got a 2-stage stochastic process here. In the first stage, either one of the marbles could be blue, the marble could be blue or it could be white. And in that first stage, the probability of a blue marble is 4 out of 9. 4 out of 9, and the probability of white is 5 out of 9. And then in the second stage, we still have the same possible outcomes, a blue marble or a white marble. But there are some different probabilities depending on what happened in the first round. Like we discussed, if I pull a blue marble out in the first round, we get all the marbles back for the second round, and so the probabilities in the second round are the same as in the first round. 4/9 for blue and 5/9 for white. If we pull a white out in the first round, then in the second, we don't put it back then. And in the second round, there's only 8 marbles. There's only 8 marbles. We started with 5 white and 4 blue. We pulled a white one out, so now there's only 4 white and 4 blue. All right, now all of these kind of second stage probabilities, those are the conditional probabilities. This one right here is the probability that the second is blue given the first is blue. And this one right here is the probability that the second is white, given the first is blue. Maybe I'll give myself a little bit more space here. This one right here is the probability that the second is blue given the first is white. That's what we found in part C. And then this last one down here would be the probability that the second is white given the first is white. Now if I multiply down each branch, if I do 4/9 times 4/9 here, that gives me 16 over 81. This is the probability that both are blue, first blue and second blue. If I multiply down this second branch here, 4/9 times 5/9, that is 20 over 81. That's the probability that the first is blue and the second is white. Down this third branch here, if I multiply the probabilities down the third branch, 5/9 times 4/8. Or actually, I'm just going to call that 1/2. That'd be 5 over 18. That's the probability that the first is white and the second is blue. And then finally, down that bottom path, 5/9, again times 1/2, would be 5/18, which is the probability that the first is white and the second is white. All right, now we want these. We want these to find what is the probability that at least one white marble is selected. And we can look at the events for our entire experiment. I guess we kind of have these events for each stage of the experiment, but the entire experiment here, these are the 4 things that can happen. I guess these aren't the outcomes though. Anyways, because we got different marbles. This is where this is one of the places where thinking too hard about the outcomes and the events kind of gets you into a little bit of trouble. At least one white marble was selected. I think in this second line we had the second marble was white. In the third branch we had the first marble was white, and in the fourth branch we had both of them are white. So these three events here and they're disjoint or mutually exclusive. These 3 mutually exclusive events are the at least one white. But we could also, if we add them together, if you do 20 over 81 plus 5 over 18 plus 5 over 18, let's see, that's 20 over 81 plus 10 over 18, which is the same as 5 over 9, which is 20 over 81, plus 45 over 81, which is 65 over 81. So that's the straightforward way of getting the job done. You could also look here at the complement. The complement for B would be the event that no white marbles were chosen. And we could find the probability of our event here by using the complement formula, 1 minus the probability of B complement. And the event that no white marbles were chosen is this 16 over 81. So 1 minus 16 over 81, which also gives you 65 over 81. So that's just another way of looking at that problem. I don't think it's super beneficial to use the complement formula in this case because we just got these 3 numbers to add up. But I suppose if you kind of recognize that from the outset, you maybe could have avoided drawing this entire tree. But we wanted to practice making some trees here. That was kind of the point of this exercise. All right, number 6. Jack has decided to advertise the sale of his car by placing flyers in the student union and the dining hall of the college. He estimates that there is a probability of 0.4 that a potential buyer will read the advertisement, and that if it is read, the probability that the reader will buy his car will be 0.2. All right, so we got 2 events here. We have the event R, where the potential buyer reads the ad. And we also have event B, the event that the buyer will buy the car, the potential buyer will buy the car. And the problem says, let's see, that the probability of R, probability that a potential buyer will read the advertisement, is 0.4. And then the second probability here that they said, if, notice there's that if there, if it is read, if the ad is read, it's a conditional probability. The conditional event is that the ad is read. The probability that they'll buy the car is 0.2. So that's a conditional probability that they gave us there. All right, finally, Using these estimates, find the probability that a potential buyer will read the ad and will buy Jack's car. All right, so the probability that they will read the ad and buy the car. This is, again, our product rule. The probability that they'll read the ad times the probability that they'll buy the car given that they've read the ad. Again, this product rule comes from our basic conditional probability formula. Or you just kind of take this and multiply on both sides by the probability of R. That's where this product rule comes from. They gave us both of those. They gave us both of those quantities, and so this is a pretty easy multiplication problem. Assuming I can do. Let's not get crazy. 0.4 times 0.2 is 0.08. So only an 8% chance that a potential buyer is going to read the ad and buy the car. Now, I think one of the things I want to point out here, there's this product rule. There's this product rule that got the job done for us in 6. Got the job done for us right at the beginning of part A, except for we kind of had to think a little bit about that. And let's see, there was another formula that got the job. I thought there was another formula that got the job done for us really, really quickly at the beginning. I guess in 2, the fact about independent events. There's some. I guess what I'm trying to get at here, not doing a very good job of, is there's some formulas. There's some formulas in this section where if you know the formulas, if you're aware of the formulas and know them, the problem is like a 30-second problem. And if you don't know the formulas, it's a problem you can spend 5 minutes on and make almost no progress, if any. And so we really do need to make sure that we are aware of all the formulas, our basic conditional probability formulas, the product rule formulas that are relevant. There are some formulas involving independent events that are relevant. And just making sure that you know all those formulas and how to apply them is a key to making a lot of problems easy, like this one. Okay, number 7. The accompanied tree diagram represents an experiment consisting of 2 trials. We got stage A or stage 1, where 3 things can happen, and stage 2, where only 2 things can happen. We want to complete the diagram and use it to find some probabilities. All right, so remember, in each stage, the probabilities have to add up to 1. And so we've got 0.5 for the probability of A, 0.2 for the probability of B, and that adds up to 0.7, which leaves us 0.3 for the probability of C. Each kind of vertex in stage 2 has to add up to 1 as well. So if A happens, then the probability that E happens given A is 0.4. The probability that E complement happens is 0.6. These 2 numbers have to add up to 1. These 2 numbers here also have to add up to 1. So that one's a 0.5. These 2 numbers here have to add up to 1. So that gives us a 0.35. All right, and then we can complete our tree diagram. I guess our tree diagram is technically complete here. We can also take some time to remember that this 0.4 here is the probability of E given A. This 0.6 is the probability of E complement given A. This 0.5 here is the probability of E given B. And this 0.5 is the probability of E complement given B. This 0.65 is the probability of E given C. And this 0.35 is the probability of E complement given C. And I guess we might as well fill in, recognize that 0.5 is the probability of A. 0.2 is the probability of B, and 0.3 is the probability of C. I think we said those things, but let's just make it official, write them on the page. We could also find the probability of A and E by multiplying down the line. This is really our product rule here. When we multiply down the branch, we're using our product rule to get it done. 0.5 times 0.4 gives us 0.2. The probability of A and E complement is 0.5 times 0.6, which gives 0.3. Notice that these two numbers here add up to 0.5. That's a thing. If we do the probability of B and E down this third branch, that's 0.2 times 0.5, which is 0.1. And then the probability of B and E complement is also 0.2 times 0.5, which is also 0.1. Again, these two numbers add up to 0.2. And then finally, the probability of C and E will be 0.3 times 0.65. I need my calculator for that one. 0.3 times 0.65 gives 0.195. And finally, the probability of C and E complement will be 0.3 times 0.35. And that'll be 0.105. Again, these values are going to add up to 0.3, and then all of these values should add up to 1 when you add them up. And you can check that they do. All right, so we got our tree diagram filled in. Use it to find the following probabilities. The probability of A, we've got that labeled in our tree diagram. That's 0.5. The probability of E given A, we've also got that labeled in our tree diagram. That was given to us, 0.4. The probability of A and E, we got that up here. That's using the product rule along that top branch, gives us 0.2. D is our first interesting one. Notice that A, B, and C, we just read things off the table and I guess did some quick multiplication. D is the first interesting one. The probability that E happens, there's a partition of E up here. Either A and E happens, or B and E happens, or C and E happens. Those are the three ways that E can happen. Those are mutually exclusive events. And so if I want to find the probability of E, I can add those probabilities together. A and E was 0.2. B and E 0.1, and C and E 0.195, and I think those add up to 0.495. Let me do a quick double check on that. 0.2 plus 0.1 plus 0.195. Yep, 0.495. Okay, we got one more question we can answer here. Are B and E independent? So the question here, there's a couple ways to answer this question, but one of the ways to answer it is the probability of B and E equal to the probability of B times the probability of E? The probability of B we were given is 0.2. The probability of E we just found, 0.495. And then the probability of B and E, here we go, ends up being 0.1. So I guess the question is 0.1 equal to 0.2 times 0.495? And our answer is no. This is pretty close to 1, but not exactly 1. Another way to answer this question, so we used our check here. Another way to answer the question is the probability of E given B the same as the probability of E? That's kind of our definition. It's kind of our definition for these events are independent. The probability of E given B was 0.5. And the probability of E itself we computed to be 0.495. So that doesn't work either. So there's a couple ways to check to see if B and E are independent. We can either go to the definition or go to this test for independence that we learned. All right, that'll do it for this supplement video. If you have any questions about any of the problems here, please send me a message on Ivy Learn. If you have any questions about any homework problems that you run across, you can also use the Ask Your Teacher feature in WebAssign.